let's go through a couple problems. It's actually one problem that I broke into two parts. This is going to be real typical for the kinds of problems that you see. I'm going to use the same system, that algorithm that I showed you, and I'm going to do that because I can't solve these problems any other way. And I really mean that. This is not just me like being stubborn. It's because this works, it's not that hard, and it's the only way I can do it. So here's how I would do it. And this is how I'm going to ask you to do it as well. So we have a model rocket launched from the ground, straight up. It's going to go up, and then it's going to come back down. It has an initial speed of 0 meters per second. It's accelerating upward at 2 meters per second squared, but its engines stop at 150 meters. Okay, and the first question is, what's its velocity when the engines stop? So here's our system. Number one, we draw a picture. Does it matter what the rocket looks like? No, it doesn't. Everything in this class, according to me, is a small box. Sometimes it's a rectangle, sometimes it'll be tilted, but it's always going to be a box. And what's going to happen? It's going to go up, and then it's going to come back down. And for this part of the problem, we're only concerned with its upward path, because it's going to go up until it gets to about 150, well, exactly, according to this, 150 meters, okay? And then what happens after that, we don't care about. We will, but we don't yet. By the way, I'm going to do this all in one color, even though that makes things a little bit less clear, but what I want you to see is what it looks like when you're doing it, and most of you are just going to work in pencil. Yeah. Rocket. That's a rocket, yeah. Okay, so there's my drawing, and I could add some information to this. I could say it starts at 0 meters per second. I could add that the acceleration is 2.0 meters per second squared. There's nothing wrong with that. And that's upward. It's an upward acceleration. But I don't necessarily have to do that. I'm going to in this case. Here's what I need to do next. I need to have a frame of reference. That means I need to know where is position 0. If this were moving in 2 dimensions, I need to know where the origin was. But in this case, I just need to know where 0 is. And I'm going to say that 0 is the ground. I'm going to call that my y dimension. So 0 meters is on the ground, and I'm going to say that my positive direction is upward. So I'm going to draw a little arrow with a plus sign. Okay. That took 10 times longer than it needed to because of the explanation. This drawing would take 10 seconds or less. All right? So that's my first step. My second step is something that you don't need to do, which is to identify vector quantities, break them up into components. We're not going to have those yet. I mean, we do. We just don't need to break anything into components because we're working one dimension. So, second step, we don't have to do in this problem. The third step is to identify our known and unknown variables. This is something I want you to do it this way, because not because this is the only way to do it, but because if we all do this the same way, then I'll be able to look at your work and in an instant see whether or not you're on the right track or not. So what I want you to do is list your variables in order of time, starting with position and velocity, then acceleration, and then your time variable. So it should always look like this. Hang on, I did that wrong because we're not using x. Okay, so you're going to have your initial position, your final position, your initial velocity, your final velocity, your acceleration, and the amount of time that goes by, your delta t. In this case, I said my axis, my one dimension is going to be the y dimension because it's vertical. You could have used x, and that's fine. I put a little y on my velocities and my acceleration to keep track of the fact that I'm looking at velocities and accelerations in that up and down dimension. You could leave all those out. You could just say v0 and v and a. All of that would have been fine because we're only dealing with one dimension. Down the road, we're going to have 2 or even 3 dimensions, so we have to keep track of that stuff separately. All right? Now we're going to go through and we're gonna put in all the values that we know. What was my initial position at the start of the problem? It was on the ground, which I've said is 0. What's its final position? Well, it gets up to 100 meters when the engines stop. So the time period that we're concerned with is that time period between launch and 150 meters. My initial velocity, it says it starts at rest. My final velocity, I don't know. That's what we're trying to find. That's our unknown. The acceleration, it's not in free fall. It's in the air, but it's being pushed upward by the engines. So it's not -10, it's 2. My acceleration is 2 meters per second squared. And then the amount of time that goes by isn't given. We don't know how much time goes by. So at this point, like, what do? Well, the last step of our algorithm says, pick an equation that is the most useful equation and use it. Our equations were, you don't have to write this down, I'm just gonna write them over here so you can see them, were that final position is initial position plus initial velocity times time plus 1/2 acceleration times time squared. Not super useful because it doesn't have final velocity in it, which is what we're trying to find. And it has time in it, which we don't have. We also had this equation. Our final velocity is equal to initial velocity plus acceleration times time. Same deal. We don't have time, and we don't have final velocity. That's one equation with 2 unknowns. Not helpful. And we had the one where you're mathematically averaging the velocities, dividing by 2 when you add the initial and final. That's equal to the displacement divided by time. Well, that doesn't help us because we don't know time and we don't know final velocity, so that's still one equation, 2 unknowns, not helpful. The last equation was the weird one. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. It's got final velocity in it, that's what we're looking for. It doesn't have time. It has initial velocity, which we know. It has acceleration, which we know. It has final and initial position, which we know. That equation will tell us everything we need to know. So that's what we're going to use. And this is where, when you write these things out, it actually is helpful to write the equation out first. So just write the equation, even if you don't like to, just write it anyway. Yeah?
Why can we use the second one again?
Because we don't have final velocity and we don't have time. So that's one equation with 2 unknowns in it.
Oh, because distance isn't time.
Yeah.
I thought distance was time.
Yeah. All right, so we're going to use this one, and I'm using, my variable that I'm using over here is y, so I'm going to rewrite it just so that we can, hang on, I'm going to put this, hang on, there's a method to this madness. I want to make this small. There. Okay, so we're going to just use this equation, but I'm going to write it with a y because that's what that's the variable that we're using. So our final velocity squared will be equal to our initial velocity squared plus 2 times our acceleration times the displacement. That's final minus initial position. And then there's some zeros here. My initial velocity is 0, so I'm just going to cross that whole thing out. My initial position is 0, so I'm going to cross that out. And then I'm going to take the square root of both sides, so I get that my final velocity should be equal to the square root of 2 times my acceleration times my final position. So that is the square root of 2 times 2 times 150, and I'm just leaving the units out here because that just makes things complicated. Yeah,
On tests, will we be given these equations?
yes.
Okay.
Yeah. So that's 4 times 150, that's 600. The square root of 600 is, I don't know what it is. So let's use a calculator to figure it out. I want to do it in my head. 900 would be 30. So it's going to be like 26-ish. No, it's going to be like 19. 25, I was close. Yeah,
Do you want exact, approximate, or both?
don't care.
Oh, okay.
Yeah, and actually, if you think about it, I know that that seems weird. If you think about it, it should make sense to you why I don't care. Because in reality, none of this stuff is really that precise. If, like it's just not. Like you think that anybody would be able to measure or tell the difference between 24.5 and 25 or something close to it. So, yeah, always round if you want to. I mean, if you want to use a bunch of decimals, knock yourself out, but I'm never going to. All right, so this is about 25 meters per second. Yeah.
How did you get rid of that first? Oh, it's a 0.
Yeah, they're 0. Okay, so that's one way to solve these problems. If you can do it, if you can do the math, if you can do the algebra, do it that way. There's another way to solve these problems. I'm going to show you right now. Okay, so this problem has a follow-up, which is this. So in this case, we're going to have really the same general setup, only we're interested in a different time period. We're no longer thinking about when it left the ground and when it got up to 150 meters. Instead, we want to know how long it's going to take to come back to the ground after the engines stop. That's this part of the time period. The part that starts here is going to keep going up for a while, then it's going to spin around and come back down, and eventually come back to the ground. So if we want to know how long it takes to come back to the ground, that has a different acceleration. Our acceleration is no longer 2 meters per second squared upward. This is in free fall. Once those engines stop, it's now accelerating at -10 meters per second squared. We can use the same frame of reference where the ground is 0 and up is positive. So here's our variable inventory. I'm going to use y again. Our initial position, final position, initial velocity, final velocity, acceleration, and time. Our initial position is no longer the ground. Now it starts, this part of the problem starts when the rocket is already at 150 meters. And our time period ends when it gets right back down to the ground at 0 meters. Its initial velocity is not 0. The initial velocity for this time period is how fast it was going at 150 meters, which we just figured out. The initial velocity is about 25 meters per second. So that's what I'm going to use. I'm not going to use 24.5. It's too many decimals. Our final velocity is not 0. Because our final velocity, while it's accelerating at this rate, occurs right before it hits the ground, not after it hits the ground. After it hits the ground, it's accelerated upward at a very, very, very large rate, which causes its velocity to become 0. Prior to that, right before it hits the ground, it's going really fast downward. And I don't know how fast it's going, so I'm going to leave that blank. My acceleration is -10 meters per second squared, and I don't know how much time goes by. All right, so let's look at our equations, and we can rule out, let's go in the opposite direction just to like heighten the sense of suspense. If we start here, then we could find actually something, but what we're looking for is time. We're trying to find how long it's going to take. This equation doesn't have time in it. Not useful. This equation does have time, but it also has final velocity, which we don't know. So this equation isn't useful. This equation has time, but it also has final velocity, so that's not useful either. Allison?
Why can I assume that acceleration is negative 10 meters?
Because it's in free fall.
I thought it starts out, it's 150 like the peak.
That's when the engines shut off. The engines shut off there, but it's going up at 25 meters a second. We just figured that out. So it's gonna continue to go up, slow down, and then start falling back down, just like when you throw a ball in the air.
Doesn't slowing down mean decelerating?
It does mean decelerating, but it has a constant acceleration of 10 meters per second squared toward the ground. On the way up, it's slowing down. On the way down, it's speeding up. The acceleration is constant the whole time. You've seen that already with the carts. We'll talk about it more because that's a really confusing thing, but it's true. In this case, there's only one acceleration the entire time. Okay. All right, so that means this is the equation we're gonna use, but we have a problem, which is that it's really ugly, and it's got a squared in it, and that's just a lot of math. So here's how you can deal with all of that. I've created a tool that you all are welcome to use called the Kinematics Solver. It's in the resources and it's in today's module. And if you click on that, then you will need to make a copy of this. Every year I do the same thing. I just change the name to Kinematics Solver -Brigar, and then don't keep opening the document over and over and over and over again. Bookmark your solver, your version of the solver, and then you can use that whenever you want without having to make a copy, all right? And then we can put the values from our variable inventory in there, and they're in order. So I'm just gonna go down the list. My initial position was 150, my final position was 0, my initial velocity was 25, I don't know my final velocity, my acceleration is -10, and I don't know the time. What are we trying to find? We're trying to identify how long it's gonna take, and we already figured out that we're using this equation. Now this looks a little weird because I can't do superscripts, but this is AT squared. This is that equation that we're gonna use, and if we click here, it tells us the time. And for those of you who remember, we have 2 times because it's gonna be a quadratic equation. That's why we're not gonna do it. We're gonna use the computer. The computer's gonna do it for us. So this would have happened 3.5 seconds prior to launch if it had been at accelerating that rate the whole time. That doesn't fit the problem. It's gonna take about 8.5 seconds to come back down and hit the ground. So that is the answer to our problem. Our time is equal to 8.5 seconds, and that's a lot easier than doing all that math by hand. Yeah?
Before our tests, would you recommend us not using it like a week before to start practicing for the test?
No. You can do either way. So we'll talk about it when we get there, but this isn't an algebra class. So there are gonna be a few mathematical things that everybody's gonna have to be able to do, and I'll tell you what they are. But if you never get to the point of being able to solve these algebraic equations, it's not gonna affect your grade in the class, because it's not an algebra class. Now, I will say that you should know how to do this. You've all ostensibly passed algebra. This shouldn't be something that you can't do, but I know some of you probably can. So I don't wanna make it impossible for you to be successful in the class. So there will be ways of dealing with it on the test. Outside of the test, you can always use the solver. All right, any questions about any of that? I know that was a lot, and that is not gonna be typically how we go about stuff, but this is like, for today, that's how we did it. Okay, so here's what happens next. There is an assignment. Most of you aren't gonna get super far. Some of you have started already, which is great. The assignment just has a bunch of sample problems. What I want you to do is start. Get as far as you can. I'll tell you when to take a picture and turn your work into the bin, and then we'll come back to this on Thursday and keep going. What you do in the next 8 minutes is due today. We'll keep working on it on Thursday, and then we'll move on to some other stuff that lets you actually get up and move.